Hi, my name is Dr. Arshad Hassan, and I'm Associate Professor at National University of Computer and Emerging Sciences, Past Islamabad. I am a graduate program coordinator at Department of Electrical Engineering, NUCES Past. I'm also Higher Education Commission Pakistan graduate approved supervisor. I have supervised many MS and PhD students. My area of interest are printed electronics, machine learning, and AI. Today, I am going to talk about merger of printed electronics and machine learning topic, which is disposable all printed electronic biosensor for rapid detection and classification of pathogens. Here is the outline of a presentation. First, I will talk about introduction and then motivation, and then I will discuss printed sensor, and then I will show you the measurement system and the detection mechanism. And in the last part of presentation, we'll talk about bacteria classification, where we have used three machine learning algorithms, which are maximum likelihood classifier, neural network, and linear discriminant analysis to classify the bacteria types. So here is the introduction. All of you are familiar with bacteria. Bacteria is single cell, very small organisms you can't see with the naked eye. So you need a microscope to see those bacteria. These bacteria can be found on most material and surfaces. Billions are in your body right now. So on the right side, you can see E. coli strain 0157H7 can make you very sick, and some of the strains of E. coli can help you to digest food. There are three basic shapes. You can see one is called bacilli, and another is called, round shape is called cocci, and some bacteria shapes are have spiral shapes. So some exist in single cell, and the other bacteria lives in clusters together. How do bacteria eat? Some make their own food from sunlight, like plants, and some are scavengers, share the environment around them. And the bacteria in your stomach are now eating what you ate for lunch. So some are warriors, like pathogens. They can attack the living things and make them sick. So, for example, the bacteria on your face can attack the skin and can cause infection and acne. So, like some of the E. coli strains are pathogenic, and some are for example, they are good to help to digest the food. So motivation behind this research is that the question is that all bacteria is pathogenic. The answer is no. So some bacteria are helpful, like lactobacillus, that can help you to make cheese, yogurt, and buttermilk, and can produce vitamins in your intestine. So some of the bacteria are good, and some of the bacteria are bad. So which can make you sick. So bacteria detection is very essential. So to make ourselves safe from the bad bacteria, electronic detection is studied in this research. So we have focused on three bacteria types. One is called Salmonella. You can see on the right side, which have flagella to move around, and another two strains are E. coli strains, which are DH5 alpha and JM109. So we have focused on three bacteria types. Here we have, you can see the shapes of these bacteria, Salmonella GM109 and DH5 alpha. The rod shape Salmonella on the right side had a diameter between 0.7 and 1.5 micrometer, and the length 2 to 5 micrometer. The E. coli strains, GM109 and DH5 alpha, are typically rod-shaped and had diameter about 0.25 to 1 micrometer and length of about 2 micrometer. So this is the measurement system we have used. We have a probe station in which we placed a sensor here, and we have an impedance analyzer. First, we drop a bacteria sample on the surface of sensor, and then we record the impedance of the sensor, and then we fed the data to the computer to where we have machine learning algorithms to classify the bacteria. So this is the system, overall system we have utilized. Now I will discuss about the printed sensor. So the printed sensor look like this one, and this is the zoomed image of a printed sensor, where you can see the we have interdigital electrodes. So if you see the interdigital electrodes, the two electrodes have a capacitor plates. So this is here we have a capacitance, and also when we drop a bacteria sample on the surface of the sensor, we have resistance between the electrodes. So we have capacitance and resistance of the sensor. So sensor electrodes look like this one, and the separation between the two fingers is 200 micrometer. We optimized this one. Actually, we have fabricated different sensors to 100 micro, 200, and then we measured the impedance, and here we get the quite well results around 200 micrometer. Usually the size of the bacteria is 2 to 5 micrometers, so it means we need 40 to 100 bacteria in series to make the electrical concentration, which is very high concentration. So to avoid this problem, we utilize silver nanowires, which have a typical length of 2 to 5 micrometers, and we deposited the silver nanowires on the surface of the interdigital electrodes. And you can see here we deposit the silver nanowires on the surface. So the detection mechanism is that the silver nanowires are between the electrodes, so it act like an open circuit. And when we drop a sample, bacteria sample, so the circuit will close and the resistance will vary. So the trend of resistance of the sensor is inversely proportional to the concentration of the bacteria. When we increase the bacteria concentration, the capacitance and resistance varies. So here on the right side, you can see bacteria concentration on the x-axis and the current on the y-axis. When we increase the concentration, the current will also increase. So it means the resistance goes down. So this is the zoomed image. Here you can see we have a printed sensor on which we deposit the bacteria and measure the impedance. And this is a zoomed version in which you can see there is spacing of 200 micrometer between the electrodes, and then we have an 18 nanowires, and the electrode width is 100 micrometer. So we drop a sample on the surface, and then we measure the impedance through the impedance analyzer. So this is the fabrication of the sensor. For fabrication of the sensor, we used inkjet printed sensor. Here you can see this is the here we place the substrate, PET substrate, boulomide substrate, transparent substrate, and this is the head, and this is the platen we have placed here, and we fabricated the silver nano ink electrodes. And then we deposit the AG nanowires using EHD system, which is an electrohydrodynamic system. Here we put the substrate on and then we deposited the Ag nanowires. The density of the Ag nanowires, we used 30 into 10 raised to power 3 per millimeter square. So after fabrication, we characterize the sensor. So on the left side in A, you can see the fabricated sensor on the PET substrate, and this is the zoomed image. And in the B part, you can see the 3D nano profile of Ag electrodes, which is showing that the thickness of the electrode is 400 nanometers, and it is smoothly deposited on the PET surface. In the C part, you can see the SEM image of Ag nanowires. So the white ones are Ag nanowires, and this is the TEM image. And in the E part, you can see the optical microscope images of bacteria. And optical images of Ag nanowires. Here, these are the Ag nanowires, and in the F part, you can see the optical images of bacteria between the electrodes. So these blacks are electrodes. Here you can see. So it means the sensor is fabricated well. So this is the overall measurement system and results. So sensor is placed in the probe station. Here you can see, and the bacteria is deposited on the surface. In the B part, you can see the zoomed image. So 10 raised to power 6 colony forming units, CFU per milliliter bacteria concentration is used. Here at this time, we have injected the sample, and we applied a voltage of minus 2.5 to 2.5 across the sensor terminals, and recorded the impedance. First, we record the impedance without bacteria to have a reference, just with the liquid material. So then this is with the culture medium, just without bacteria. And then we use different concentration, bacteria concentration, like 10 raised to power 6, 10 raised to power 7, 10 raised to power 5, and 10 raised to power 4 CFU per milliliter. Actually, you can see we have injected the sample here, and the impedance varies along time. When we injected the sample on the surface, the bacteria interacts with the Ag nanowires and makes electrical connection, and the impedance varies. So after 8 minutes, the impedance is stable. So that's why we taken the value at after 8 minutes to make the stable readings. So these are the measurements for 3 classes. On the left side, you can see for DH5 alpha. In the middle, you can see for in the middle, you can see for JM109, and on the right side, you can see for the salmonella. We have applied a sweep between minus 2.5 to 2.5 and recorded the current values for 3 bacterias. And we have total 251 current points when we applied a voltage from minus 2.5 to 2.5. Some of the measurements are discarded because we have a shorted sensor. So here you can see some of the data is discarded. Actually, we have measured 40 readings for each bacteria, and 45 for each bacteria, and 5 are discarded. So we have left with 40 files, 40 for each file. So we have total 120 files of data. These are the impedances against the bacteria concentration. First, you can see the impedance variation against the Salmonella concentration. In the B part, you can see the impedance variation against the GM109 concentration. And in the C part, you can see the impedance variation against the DH5 alpha. And this is the comparative analysis with the blank one, which when we have no bacteria, so just a medium. And these measurements are recorded for 10 raised to power 6. And then we extracted the features from the measured data, like for these graphs, we have 40 files. So we have 40 measurements. So, and we recorded the current and we divided the current into 251 features. And for each class, we recorded 251 features, and we have 40 measurements. So these are the vectors we have recorded, and then we have extracted some of the features. For example, we took the data and take the first derivative, like recording the slope of the data, which is another feature. And then we analyze those features, like, for example, we analyze them from 116 to 126, first derivative and second derivative. So it looks like this one. So you can see that the impedance is overlapping, and it's very hard to distinguish between the bacteria. So that's why we utilized machine learning algorithms to classify the bacteria. So first we used maximum likelihood estimation, in which we just took two features, 125 and 126, and then pass it to MLE classifier. So in MLE classification, these two features are used. So on the right side, you can see that this classifier, you can see that you have three distinguished classes. Actually, the plus sign indicates the mean, and the circle is indicating the covariance of the class, each class. So we have used 70% of the data to calculate the mean and covariance, and then we have created a ML model and then passed mean and covariance to classify the bacteria. So here on the right side, you can see we have three distinguished classes. One is the GM109 and DH5 alpha and the Salmonella. On the x-axis, we have one feature, and on the y-axis, we have another feature. So 70% of the data is used to calculate the mean and covariance for each class. And then the ML model for each class is created, and we pass the ML model and mean of each class to Bayesian classifier, and scatter plot is used to plot the data on the previous slide. So, and then we plot the line based on the variance of each class. So Bayesian classifier returns the posterior on which the class labels are decided. And lastly, we use Kerr confusion matrix to find the accuracy, and we achieved 100% accuracy with only two features. So this is the linear classifier V. The next one, we used a non-linear classifier, which is backpropagation neural network. So in backpropagation neural network, the configuration consisted of an input layer, hidden layers, and output layers. So in backpropagation neural network, we used 10 hidden layers, 3 output layers, and the data is divided into 70% for training, and 15% for testing, and 15% for validation. Actually, we have 120 data vectors for which is 100% data. And from those, we used 84 data vectors as a training, and the remaining 36 which we used for testing and validation. 18 for testing and 18 for validation. And 10H is used as an activation function, and the accuracy is also carried out by square confusion matrix. So here you can see we have a data of each class, and we have 40 measurements against each class, and then we pass the data to the neural network. And then we have 10 hidden layers and 3 output layers, because we have 3 classes, so that's why we have 3 output layers. So on the right side, you can see the training data is 70%, and the validation is 15%, and the testing is 15%, which is 84 samples for training, and 18 for testing, and 18 for validation. These are the confusion metrics for training, validation, and testing. And last is the all confusion metrics. So in the training, you can see we have total 84 samples which are correctly classified, and then we have a validation 18 samples, and then we have testing 18 samples. And on the right side, you can see we have accurately classified all the samples. The last one is the linear discriminant analysis. In linear, we have used a scatter plot on the x-axis and y-axis represented 2 IV features. First, we distinguish class 1 and class 2. So here you can see the first we distinguish between GM109 and DH5 alpha. And in the second part, we used hyperplane between class 1 and 3 to distinguish between class 1 and 3, between Salmonella and the DH5 alpha. And the third part, we distinguish class 2 and class 3 between GM109 and DH Salmonella. So the Salmonella, you can see the green one has a high variance, which is 47% variance, and the blue one, which is E. coli, and the red one, which is DH5 alpha. So the E. coli has GM109 has 19% variance, and DH5 has 34% variation. So you can see the results of DH5 alpha, that there is clear separation between the 3 bacteria groups. All the testing samples are well clustered along the hyperplanes. So the achieved overall accuracy is 100%. So you can see the classes are well separable. So these indicating the 100% accuracy, indicating the accurately discrimination of bacteria types. So all bacteria, all the algorithms achieved 100% accuracy. So here is the conclusion of the presentation. Sensor is very sensitive and produce a high resolution. You can see that it shows the variation against the small concentration. Sensor is reusable. Lab on chip can be made by deploying sensor array. You can see the high accuracy in maximum likelihood classifier, LDA, and neural network due to good feature selections. And second reason is that the data size, sample size is very small. So in future, the accuracy can be investigated against the sample size. So we can investigate if the data size is scale, then what is the effect on the accuracy. So this is the conclusion. So these are the references. And thank you very much for your patience and listening. If you have any questions, you can ask, please. Thank you.